there are all kinds.
No, I'm sorry, later.
That doesn't sound. Is that echoing? No. I think it's okay. Anyway.
Yeah.
So one of the things that I wanted to mention is about questions, and questions or discussions or whatever. And my only problem is the older I get, the worse my hearing is, and some of you know about such problems. But if you have questions, either I can try to hear them, or this room being small enough, that might work, or you can ask afterwards and we can come up and have a discussion. I'd love to do that. But today, I want to talk about James Clerk Maxwell. And this man is regarded by those of us in the profession of physics as the equivalent of Isaac Newton or Albert Einstein. I mean, he is of that importance. And yet, while both those people, particularly Einstein, of course, is extraordinarily well known to the public, Maxwell is certainly not, and he's a much more obscure picture. But this is a great pity, because much of our present modern world, certainly the electrical part of it and the thinking behind the electrical part of it, comes really from Maxwell. He opened up the entire world of communications, of electronics, of electricity, in ways that few people have done. And that's why I put this quote in from Einstein. Few men have ever, and I wish he had said people, but in this world have such an experience been vouchsafed. And this is also true that an entire epoch of science that started by Isaac Newton was terminated really by Maxwell, and the whole of modern physics really began with him. Isaac Newton, well, in today's world, physics, all sciences are sufficiently complex that there are people who do the theoretical part, which in physics is all mathematics, and people who do the experiments, which is the reality to see whether these mathematical theories are valid or not. And those are pretty separate professions. I did experiments in my life because I love mechanical things, and it was great fun to do. But Isaac Newton was a man who is capable of doing everything in his field, and so was James Maxwell. I have a picture. Where is my, there, a picture of him as a young man, about 20 years old. That his work involved major contributions to our understanding of how colors work. One of the great things he did was explain what goes on the rings of the planet Saturn. And he did this in 1859 and explained what they were. And we couldn't prove what he did until the Voyager satellite in 1980 sailed past the planet Saturn and could photograph the rings up close, showing that his work 100 and some years before was in fact correct. It's truly remarkable. He contributed major work to the theories of fluids, and along with Ludwig Boltzmann, he derived the molecular theory of gases. And this was in the days when there were lots of very serious people who didn't even believe in the existence of atoms, yet he had a whole mathematical theory. Yet it was his work on the theory of electromagnetism that puts him amongst the great immortals in science. And he gave the world a completely different outlook on things. He replaced what Newton did was talk about, as I mentioned yesterday a bit, he talked about particles, about objects, about masses, about forces, but he had this terrible problem of explaining how forces interacted, how my favorite example, how the Earth knows the sun is out there exerting a gravitational force on it 150 million kilometers away. And so since he didn't understand how that worked, he just said it works. But what Maxwell did is he introduced a whole new way of thinking of it, and he replaced these what are called action at a distance forces by an abstract world of gravitational or electromagnetic fields, a changing of space itself. Which I will try to talk about as best I can today. And this has taken a very long time to understand, but it is a very mathematical way, yet it's not as esoteric and mathematical as, say, the theory of relativity of Einstein. Yet Einstein, of course, achieved superstar status. It's hard for me, at least, to realize that in the 1920s, Einstein, as I'll talk about on Friday, was as popular as, say, the Beatles were in 1960 and 1970. There were tens of thousands of people who showed up in New York when he arrived on the ship from Germany. It's just, for a scientist to have that kind of notoriety really boggles my mind. He was born in 1831, at almost exactly the same time when, as I mentioned yesterday, Michael Faraday was pushing a magnet into a coil of wire and creating a current. He was born, he's a Scot. He was born at a place called Glenlair, which is in the county of Dumfries and Galloway, which, if you know Scotland at all, is in the far southwest corner of the country, right up against the English border. Faraday, as I mentioned yesterday, was born quite poor and had quite a struggle in life. Maxwell, on the other hand, was born into the family of a landed gentry, quite a wealthy family, and it's a family that had connections back to the time of Mary, Queen of Scots. The British Prime Minister, Robert Peel, was a family friend, as was the author Walter Scott. It was a very famous thing. A great uncle of his was a collaborator of James Hutton. And Hutton was a man who, in 1785, wrote a book called The Theory of the Earth, in which he invented the whole modern science of geology. One of my favorite stories is his grandfather was a naval captain in the East Indian Navy. And at one time, his ship was shipwrecked off the Bengal coast. And he managed to swim to shore supported by floating on his bagpipes. And when he got to shore, he took the bagpipes up. There were a few other survivors, and he began to play very loud on his bagpipes, which sounds really a terrifying thought. And it cheered up the fellow sailors and also apparently frightened off the tigers. So it had all kinds of benefits. His name was Clark, but his wife was a Maxwell, and so he put both those names together, and so when he had a son, his son John was John Clark Maxwell, and John Clark Maxwell married a woman named Frances Key, and their child was James Clark Maxwell. And he was born when they were quite old in those days. His father was 42, his mother, Frances, was 39. and they had married late, but they had had a girl child earlier named Elizabeth who had died quite young. So James was really an only child, and he had quite a happy childhood, unlike Faraday. But then when he was 8 years old, his mother developed stomach cancer and died, and that made life very hard. His father hired a tutor to educate him, but the tutor was harsh, and James did not like him. And so eventually his father, who was rather a stubborn man, sacked the tutor and sent James off to school in Edinburgh. Now, Dumfries and Galloway is fairly far from Edinburgh, and so he had rather a rural accent and was badly teased at school. But then, like Newton, he got into a fight with a much bigger boy and thrashed him, and that earned him a fair amount of respect at school. He was fascinated at school by geometry, and this is apparently not uncommon amongst people very talented in mathematics. It certainly was true in childhood of people like Blaise Pascal or Albert Einstein or Bertrand Russell, all of whom were very great mathematicians. He was a very successful student at school, and his father was so impressed that his father also moved to Edinburgh, and he took him to meetings of the Royal Society of Edinburgh when he was 14 years old. And he was interested and successful enough there that at age 14, he published his first piece of independent research on the geometry of ellipses and oval curves. And this was so well done, it was said to be better or simpler than the mathematics of René Descartes, who invented the mathematics of ellipses. And it got published in the Journal of the Royal Society. Not bad for a 14-year-old kid, I thought. He had an interest in philosophy in his early age and read Thomas Hobbes. And this again seems not so uncommon amongst young people. Einstein was reputed to have read Immanuel Kant's Critique of Pure Reason when he was 13. I find that hard to imagine, having struggled with that book. He came from a rather religious family and was a serious churchgoer his entire life. They always said grace before meals. Both his parents were serious church attendees. Now, a particularly exciting event happened when he was 15 years old. This is 1847. And the planet Neptune was discovered. It's the most distant planet in the solar system now that Pluto is no longer considered a real planet. And just if I can go through that for just a second, William Herschel had discovered the planet Uranus back in 1781. And then there were observations of it over the next 50 years, and its orbit was not perfectly elliptical. It moved from that. And so it was suggested there might be something else out there whose gravitational field was disturbing it. And this, of course, is the planet Neptune. Now, to calculate what happened in these days when there were no computers, of course, for several hundred years, it was a very serious problem. But a young Englishman named James Couch Adams did a calculation and located a planet, but he couldn't get any British astronomers to actually look where he suggested it. The very next year, a Frenchman named Urbain Le Verrier did a similar calculation, not knowing that Adams had done this, and he managed to get the Berlin Observatory to look for it. And of course, they found the planet exactly where he suggested. That made a real hullabaloo where the British then said, oh, but Adams did it, even though they wouldn't look for it. They wanted to claim Adams. And there was a lot of fighting over the next few years, for which Adams fortunately stayed far away. But there was a competitive mathematical Adams Prize that was created in his honor. And 10 years later, Maxwell won that prize with his calculations of the rings of Saturn, which I will again get to. But the 15-year-old Maxwell was deeply impressed by the fact that you could do such calculations and figure out really what was going on. Now, he had a lifelong interest in optics and particularly in colors. It was well known by Maxwell's times, following the work of Thomas Young in London, of Auguste Jean Fresnel in France, Joseph von Fraunhofer in Germany. These are incredibly famous names to anybody who has studied physics. But they had shown that light was indeed a wave phenomenon and not a series of particles such as Newton had assumed. Now, waves come in two types. In a wave, something is moving, waving. And there are two types. There are sound waves, so that the vocal cords in my throat vibrate, and they make the air molecules move, and the air molecules move from me to your ear, and they move on my hearing aids or in your eardrums, and that gets converted by our brains into what I hope is intelligible sound. But the air molecules move from me to you, and they go this way, along the direction of the wave. That's called a longitudinal wave. But there are other kinds of waves, like a string wave. In a string, if I hold the string taut between us and I shake it, the bulge moves, but the string molecules go up and down. And so they move in a direction perpendicular to the direction of the wave. That's called transverse, a nice word for Latin word for perpendicular. Besides this optics, which was really a hot topic by 1840, another area of great interest was called thermodynamics. Thermo for heat, dynamics for motion. So it's the field of heat and motion, or heat and energy. And the reason this was really a hot topic, so to speak, in those days was because in the end of the 18th century, James Watt had invented the steam engine. And that had caused the Industrial Revolution and had made the growth of our modern economy. It also, of course, has some less pleasant parts. The first of which was the working conditions of the people at the time of the Industrial Revolution, which were dreadful. And we have problems today of global warming due to all the burning of fuels. But still, it certainly has made the modern and much more comfortable world. Now, in the 1840s, when Maxwell was still a child, the Germans like Robert Meyer and Hermann von Helmholtz, and the English James Joule, again, very famous names, had showed that heat was just a form of energy. And the whole idea of energy was really becoming important and popular in the 19th century. And the energy, the unit of energy today is named the joule after James Joule. And the most significantly important law in all of physics is the law of the conservation of energy. Energy, whatever that word means, is a substance that can be transformed, or a thing that can be transformed from one to another, from mechanical to electrical to thermal or whatever, but it cannot be created and it cannot be destroyed. There is a finite amount and it is conserved. But another important quantity involving energy is its availability, not just its existence. So that, for example, when you buy petrol for your car, only about 20% of that petrol that gets burnt moves the car. 80% of it, of all the money you spend on petrol, goes out the exhaust. Okay, a very unpleasant thought. I always think when I am holding that handle. Lights, the electrical filament light that most of us know about, only 10% of that is actually light, and 90% of it is heat. And of course, they are very hot. And this is why in the United Kingdom, you can hardly buy those kinds of bulbs anymore. And they're being replaced by light-emitting diodes, which are about 50% efficient. So half of it. Yes, ma'am. I'm sorry, I can't.
She's saying you can't buy them in this country either.
Damn. Being deaf is really a curse, let me tell you.
Lady said we cannot buy them here.
Oh, you cannot buy them. You can't buy them here. Ah, good. That's a very good sign. Thank you. And I'm terribly apologetic about my hearing, but yeah, it's very hard. What I could find was these here, which I can't get in England, are these small bulbs with the little pins that you can put in. You can't buy those either in Britain, but I bought a half dozen here so I can take them back. Because the LEDs last forever. I don't, but they do. So I'm slowly replacing them, but it's expensive to do, but they're very much less expensive to run. They save a lot of money on your electric bills. Anyway, the availability of energy is measured by a physical quantity called the entropy. And it has been shown that entropy is really a measure of disorder of a system. So, and these concepts of conservation of energy and entropy are in the first two laws of thermodynamics. And the first law is the conservation of energy, that you cannot create it or destroy it. The second law is that not all energy is useful and some of it gets wasted. However, these laws also, because they are so important, have a common language sense or common parlance. The first law says that you can't get something for nothing. And the second law says, well, you can't even break even. There is even a third law of thermodynamics, which has a popular statement, which would probably say, the harder you try, the worse you do, which is part of, I'm afraid, of real life. But the second law has very profound implications, because it says that all systems run down. Human life comes to an end. Our sun, which will live some billions of years, nonetheless, will burn out and turn into a cold, dark cinder at some point in the far distant future. And if this law applies to the entire universe, which we don't know, then the whole universe will become a soup of individual particles all moving at some cold temperature. And all of these ideas about thermodynamics were developed during Maxwell's lifetime. At 16, he left school and was enrolled in the University of Edinburgh. He was an outstanding student, and in his day, in our day, there are lots of very good universities in the world if you want to study science or mathematics. But in his day, in Britain, there was only one university that was really well known for that, and that was Cambridge University. And so his professors were so impressed, and at the University of Edinburgh, were so impressed that they traveled off to Dumfries and Galloway to talk to his father, to convince his father to send James down. Turn this blasted thing off. To send James down to Cambridge, and eventually he relented. And so at 18, James went down to Cambridge. He was extraordinary at that school. Oh, I never showed you the house he had. That's the house in which he grew up. I put the color picture in because he invented color photography as well as and we'll get to that. He made the first color picture in the world. This is his tutor at Cambridge, making this statement about him as being incredibly brilliant. His intellect got him elected to what is called the Cambridge University Select Essay Club. This was a very significant Cambridge intellectual club, which had allowed only 12 members in it, not surprisingly called the Apostles. And members in other periods were people like Lord Tennyson, Alfred North Whitehead, Bertrand Russell, etc. So very significant people. And he wrote numerous essays and scientific papers for that. But he got quite ill working with something in the Victorian times called brain fever, whatever that is, and had to go home to Scotland for a while. He did extraordinarily well, graduated with a first-class degree, not surprisingly, and was hired on as a don by the university. And the life there suited him really very well. In the summer of 1854, when he was 23 years old, he took a summer holiday with his relatives on his mother's side, the Key family. And one of them was a very beautiful young girl, aged only 14, he was 23, named Elizabeth Key. And she was considered very mature. After all, girls of 15 and 16 got married in those strange days. And they spent much time together, walking together, and apparently fell deeply in love. And there was, for the next year, a passionate set of letters that passed between them. But the families killed that romance because of the problems of consanguinity, since they were first cousins. So he returned to Cambridge and the relationship ended. In March of 1855, he made his first really serious paper called Experiments on Color as Perceived by the Eye with Remarks on Color Blindness. And what he did was to invent the Maxwell's color spinning top, this color wheel. If you spin this quite rapidly, okay, the light that you see reflected from it will look white, okay? And any color can be made by spinning pieces of colored paper together. So if you spin red and green together, you will get yellow to the eye. It works with light. It does not work with paints or colors. They work differently. But Maxwell showed that any color can be made from 3 primary colors. And our eyes, of course, as many of you will know, contain cone cells, which are more in the center of the eye. And these are cone cells have different color responses, and they're broad response, but they peak in red and in green and in blue. And so color blindness only means that one of those three sets of cells is missing. And so of those three colors, you can make any color that we can see. In October of 1855, he was hired on as a fellow at Cambridge, which is a significant thing. But in 1856, his father died. James had been brought up with this rather Calvinist Scottish religious tradition, so he was not a terribly emotional person, but because his mother had died young, he and his father were very close, and so his father's death was really very hard for him. And he wanted to be back in Scotland, and so he left Cambridge and took a job at the University of Aberdeen in what was called Marischal College in his day, and this was in April of 1856. And one of the problems that he worked on when he was in Aberdeen was about the rings of Saturn. The rings of Saturn had been first noticed by Galileo with his telescope. He looked out at the planet Saturn and he saw a bulge in the middle of it. And only about 50 years later, Christian Huygens, who had a Dutch scientist, had a much better telescope, and he could see that it wasn't a bulge, but it was a ring. And certainly by the 19th century, the rings of Saturn were well known, including that dark band in between the rings. Now, the question is what the rings were. Okay, what were they made of? And that problem had been studied for the first half of the 19th century. And what was clear was that these rings could not be solid, because if you look at a particular ring here, there's a huge gravitational force, and the force is very strong here and weaker here. And because of the difference, if the ring was solid, the gravitational force would have pulled it to pieces. And so there was a question about what the rings were actually made of. And so the Royal Society Cambridge University offered a prize, the Adams Prize, for somebody who could solve what this was. And that excited Maxwell, and so he started to work on it. He worked for 2 years on that problem, and in 1859, he published a paper called On the Stability of the Motion of Saturn's Rings. That paper was 90 pages long. I have never read a science paper that was 90 pages long. Reading papers in the physics journal takes me about an hour per page, so 90 pages would have taken me a month. In any case, what he predicted, this is published in 1859, that the rings of Saturn were composed of individual rocks, not one solid, but floating rocks. That's 1859. In 1981, 122 years later, NASA published results from the Voyager 1 spacecraft close enough to see the structure of the rings. And there's the structure of the rings, just as Maxwell had predicted. Individual rocks, just remarkable. One of the great mathematicians of the 19th century said that this publication is one of the most remarkable applications of mathematics to physics that I have ever seen. He won the Adams Prize for this work, as I said. In June of 1858, he married a woman named Catherine Mary Dewar, who was the daughter of the principal of Marischal College, where he was teaching. She was 7 years older than he was. She was taller than he was, and his family thought that he could do better, as families, I think, often do. She was quite aware of the fact that he had been in love with his cousin earlier, and aware of the fact that his family didn't like her very much, and she did not like them either very much. It was the idea of swarms of small rocks floating around perhaps led him to consider gases as his next thing. Now, at least 100 years earlier than Maxwell, the great mathematician, Swiss mathematician Daniel Bernoulli had proposed that a gas consists of a myriad of small atoms that are moving randomly around, and that they are banging on the walls of the container, and that banging force on the walls is what we call pressure. And the banging of molecules on the walls is in fact what we understand by pressure. And in an airplane wing, the banging of molecules, more molecules on the bottom of the wing than bang on the top of the wing, is what holds an airplane of several hundred thousand kilograms up in the air, something that always astonishes me when I'm flying in an aircraft, that it's only being held up by these tiny little molecules that are bouncing off the bottom of the wing. Not something of great comfort, I'm afraid. The number of molecules is inconceivably large. It's so large that the difference of a few trillions of molecules is minuscule. Okay, and so the idea of trying to deal mathematically with these molecules is just impossible. And so all we can do, and what Maxwell introduced, was a means of treating these things in a probabilistic fashion. So he introduced for the first time the ideas of probability into a discussion of physics, and created something called the probability of a molecule having a given velocity, and something is known as the Maxwell distribution, which is taught to every undergraduate in any technical field. And this paper was published in 1859. In an article called The Illustrations of the Dynamical Theory of Gases. And in the same year, he published on the theory of color vision, and it was there that he postulated what we understand about origin, about addition and subtraction of colors. And 1859 was also the year in which Darwin published The Origin of Species. So that was quite some year in science. And just to talk about that for a minute, the theory of evolution led to a lot of arguments, and they were not religious arguments, they were scientific arguments about evolution, because evolution takes a long time. And geologists said that the Earth had not been around long enough for evolution to take place. It was more than 6,000 years old, as perhaps some religious people thought. But it wasn't because the Earth had been molten and was now solid, they could calculate how long it took to cool down, and that wasn't long enough for the hundreds of millions of years for evolution. And so for a long time, from 1859 on, for at least the next 30 or 40 years, there was a terrible argument and an argument between geology and biology about what really had taken place. And the problem was the geology was wrong about that. And the Earth really is 13.7 billion years old. And the reason was because geologists did not know, but there was this phenomenon called radioactivity, which wasn't discovered until the 1896. And radioactivity, yet again, E equals mc squared, the world's most famous scientific formula, means that there was radioactive decay, energy was released in that radioactive decay, that energy in the center of the Earth caused the center of the Earth to stay molten and hot, and that meant that the Earth was hot for a very long time, several billions of years, and plenty of time for evolution to take place. Now, there was a problem, though, the very next year, 1860, because Maxwell's job disappeared. There were two colleges in Aberdeen, and in 1860 they were put together, and there weren't enough jobs for everybody. And so it became the University of Aberdeen from King's College and Marischal College in Aberdeen. And so Maxwell lost his job. He applied for a chair at the University of Edinburgh, but another very brilliant Scottish scientist named Peter Tate also applied for that job. And Tate was a good teacher and Maxwell was a dreadful teacher. And so Tate got the job and Maxwell did not. And so he, undeterred by any sense of failure, he applied for a job at King's College in London, and he got that quite quickly. It had a fairly serious teaching load, and as I said, he tended to get not be very good teacher, and so it was a hard problem for him. It is interesting that in the Victorian times, there are an awful lot of letters that are still in existence between him and his wife. And they are very prosaic letters. There's no passion, there's no love, there's no emotion or anything in any of these letters. And whether that's indicative of how they were, or it's just because of the Victorian times, people didn't do that, nobody seems to know. But his work continued to be exceptional. And in 1861, he invented and displayed the very first color photograph ever, something also that he managed to do. And his publications on color won what is called the Rumford Prize, which is offered by the Royal Society, which Rumford had helped found. And it's interesting to compare Maxwell, who was a very devoted and loyal husband, with Rumford, who was originally American and quite a rogue, and who had many, many affairs. And so while Maxwell seemed to have been a very faithful husband, back 40 years ago when he was still alive, Rumford's wife carried a bucket of boiling water out of the kitchen and poured it all over his prized rose beds to kill them. So she was a very angry woman, and justifiably so. In the 1850s, Maxwell grew a significant beard, something that people liked in those days. Now, in those years, 1861 to 64, Maxwell did his really greatest work. His Maxwell's equations were first published. People like me who give popular lectures about science are told that every time you show a formula, you lose half the audience immediately. So I'm always nervous about showing formulas. However, I do it anyway. And I'm going to show you the most difficult formulas I've ever come across, which are Maxwell's equations. And mathematics is a language, and it's a foreign language, and it's a difficult language, but it's a wonderful language because it has no misunderstandings. One of the things I have learned in dealing with a partner, a wife, is to try to, when I hear something that wounds a bit, and I try to ask, is what I heard is that what you meant to say? That can't happen in mathematics. It's either right or wrong. And if it's wrong, it goes away. And so I wanted to show you these equations. And these things, well, this number, E, is the electric field. B is the magnetic field. So this is electricity, this is magnetism. Maxwell invented that. He just didn't know what letters to use, and so he used A, B, etc. But there are constants here. These Greek letters, the Greek M, the Greek E, mu, and epsilon. And these are constants that get the units right, okay? But what he found, which was so incredible, he's talking about electricity and magnetism. And if you take these two things, which are just numbers, right? You take them and you put them together and you get the speed of light out of it. C is the common number, like in E equals mc squared, is the square of the speed of light, coming out of just sort of magic by getting the units right, just as if you were trying to get degrees Celsius to degrees Fahrenheit and at some constant number. So something about electricity and magnetism deals with light. And nobody had understood that before Maxwell. So that's why I put these equations up. I mean, this is all gobbledygook, but it's nonetheless. You can, one of the things that can be done even without the math is to appreciate the significance of what he has accomplished. This is a human being, it's a human thought, human created ideas. One of his biographers equates an understanding of the genius involved in this kind of thing with so trying to understand a great artwork. So that, for instance, you can appreciate a Rembrandt painting without worrying about what his brush strokes were or where he bought his paints. And we can try to appreciate the genius of a man like this and his ability to create something that suddenly wind up by relating electricity and magnetism to visible light. It always seemed a dreadful shame to me that often very intelligent people who just refuse to think about these greatest of intellectual achievements, even though they can appreciate works of art or works of the humanities. I just think that's a dreadful shame. Maxwell's work is a turning point in the human view of the universe. And it's a revolution in thinking. The introduction of this idea of electric fields and magnetic fields, the changing in space. You can buy a t-shirt these days, which has that on it. I've never had the courage to do that, but you can, in fact. The Nobel laureate Richard Feynman has put it in a different way. the most significant event of the 19th century will be judged as Maxwell's discovery of the law of electrodynamics. Now, he's an American, so he talks about the American Civil War will pale into provincial insignificance, except it may break out again in this century, but we don't know. However, I disagree with him because he's leaving out Darwin's theory of evolution, which is also a very significant event in the 19th century. Oh my goodness, okay. I've got about another 40 minutes, so I'll skip some things. As I tried to talk about yesterday, the invention of the battery changed our understanding of the world of electricity and magnetism, and led to a great deal of interest. And the idea that an electric current could affect a magnet, and so Faraday found that a magnet could in fact affect an electric current, but only if the magnetic field is actually changing. Now, when Faraday looked at the pattern of iron filings and thought that space really was changed by the existence of the magnet, and because he had no mathematical ability, really, was just a brilliant experimentalist, he could not do something. But Maxwell was a tremendously brilliant mathematician, and so he then really also thought that the presence of the iron filings was a perturbation in space itself, so that space was not empty, but was filled with something, to which he gave the marvelous Victorian name of the luminiferous ether. And it was this luminiferous ether which allowed the waves of light to be transmitted from the sun to us, and also somehow to be responsible for the force of gravity. There has to be some, if there is a wave waving between the sun and the earth to carry the sunlight, there has to be something to wave. What could a string wave be without a string, or water, which I was watching the ocean from my flat where I'm staying this morning, which is quite wild and full of waves. What would a water wave look like without water? I mean, it's inconceivable. There has to be something waving. And so for Maxwell, it was this luminiferous ether that is waving. But it's a peculiar substance. It can't be sticky, because the light which is making it vibrate up and down comes from tremendously far distances away. And so if it had any sort of stickiness, then the light wave wouldn't transmit over large distances. Also, it had to have zero friction, because the Earth is moving through it around the sun, and it's not slowing down. And so it can't be rubbing on anything. So it's a very peculiar substance. What we will see on Friday is that Albert Einstein says it's such a peculiar substance it doesn't exist. And that makes the light very strange stuff. But Maxwell's genius is he comes up with these statements: light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena. I'm sorry, it doesn't seem to exist. And light is just an electromagnetic phenomenon that has both electric and magnetic properties which wave. and they wave in a direction which is perpendicular to the direction of travel. So what he's saying is that light waves are transverse waves, just as string waves are. Okay. Now, what Maxwell is doing is saying that light has these fields in it. It has an electric field and a magnetic field. So he has created the first of the modern variety of field theories which we have today. The distance between the peaks in a light wave is extraordinarily small. It's extremely tiny. And that's why it took such a long time for us to understand that light was in fact a wave. You can tell yourself that light is a wave because waves, when sneaking through a small opening, will spread around in a phenomenon called diffraction. And it is quite possible to take your two fingers, it's not easy, but it does work, and look at a bright light source and put them almost touching together. And just before they touch, you can see a bunch of black lines and white lines. And that's really a sign of the wave nature of light. So it's quite a remarkable thing. But there must, if light is an electric and magnetic wave or an electromagnetic wave of a given wavelength between peaks, there must also be shorter and longer ones, and there are. They're called microwaves and radio waves and television waves and X-rays and gamma rays and all sorts of other waves, some of which have very long wavelengths and some of which are not. So the idea that light was composed of fields and waves and so forth was an enormous change, and it was changed all of the way in which scientists think about the world. And it was what philosophers of science like Thomas Kuhn call a paradigm shift. And it's like in Hans Christian Andersen's story, you know, the child comes along and says, look, the emperor has no clothes. And everybody realizes that the world has to change. So Maxwell is the first person really to overshadow, to foreshadow the modern scientific ideas of space, time, and matter. The problem with us on understanding science is that we have an intuition that is built up from childhood. And our intuition is based on objects that are this size. It's centimeter size, meter size. But the world of atoms and the world of galaxies is so incredibly different in size that the rules which they have to obey are completely different than the rules which objects of this size obey. And so the only language in which we can understand them is this foreign language of mathematics, which is hard to learn. Maxwell had gone back. He had left Cambridge and left King's College and gone back to live in Scotland. But then in 1870, the Duke of Devonshire, whose name was William Cavendish, gave a lot of money to the University of Cambridge to build a laboratory at the language and create a chair of experimental physics. And that was offered to Maxwell. And Maxwell's job then over the next several years was to build this new laboratory, which is called the Cavendish Laboratory at Cambridge University. And he was involved in the design of the building and of all the equipment that was put in. And it was quite an important job. And It took him several years, but of course, the Cavendish Laboratory at Cambridge is the place where in 1895, the electron was discovered by J.J. Thomson, and in 1953, Watson and Crick discovered DNA. So it has become a very famous place indeed. Maxwell, as I said, was a deeply religious, rather devout man. He believed very firmly in the immortality of the soul. But by the spring of 1877, he began to develop heartburn, and he had difficulties with digestion, took lots of sodium bicarbonate. By the end of the next year, 1878, he had trouble. He couldn't do much work, and by the end of that year, he had difficulty in swallowing and was in a lot of pain. He went back, of course, he went back to Scotland. His mind was affected. And he was told in October that he was suffering from stomach cancer, the same illness that had killed his mother. And eventually he died in November, the 5th of November in 1879. He was 48 years old. Like so many great people, he was not buried in Westminster Abbey, but rather in the common family grave at his, a picture of a light wave, which I didn't show you, but never mind. The tombstone, his father at the top, his mother, James, and then his wife. All buried there. She outlived him by several years. And finally, the importance that physicists imply to Maxwell is shown in the following cartoon, On the Shoulders of Giants, Newton's phrase. There's, of course, Mr. Einstein with his ideas of time, but based on Maxwell's field theories and the mathematical field theories that he first created. So I think stop at that point, having used up an entire hour. But thank you very much. And if there are any discussions or questions, we can try to do that after. Thank you. Tomorrow, I want to talk about Marie Curie, a phenomenally interesting woman, also one of my geniuses of science.
Wasn't her husband to Madame Curie's husband? Madame Curie's husband was also a giant.
He was also a physicist, yes. And this poor woman, she had one hell of a time because all of the work that she did after he died was due to him. She got very little credit.
I have a book. She was meant to be the most brilliant woman of the 19th century.
Well, mostly of the early 20th century, but of the late 19th, and she was an incredible scientist. She won 2 Nobel Prizes, not 1, 2.
And she also did with milk, so it wasn't poison.
She probably died of a radiation exposure. She played it. She did a huge amount with radioactivity, and way before anybody knew that there were problems of you needed to be careful about radiation.
So that was very nice. Thank you very much.
Oh, it's a pleasure. Thank you for coming.
See you tomorrow.
I'm looking forward.
Oh, you were talking about the stars and the light.
Yes.
In the observatory, have you been there?
Oh, yes.
No. The students at University of Western Cape and also